So last time we have discussed that in general I need a mechanism between the load and the motor in order to shape the power. You know that most of the mechanical loads does not demand such high speed. The electrical machine is compact. Yeah? And if the machine is compact, this means that the shaft will rotate in very high speed. For example, the synchronous speed is dependent on the frequency, so it can reach to 1,500 RPM in 4 poles and 3,000 RPM in, let's say, a 2 poles machine. Yeah? Now, if this machine is installed to lift up an elevator, the lift here or elevator, I don't need such speed. Now, our elevator here is, let's say, transmitting within, I think, 1 meter per second. That's not fast. So in this case, I need what? I need a mechanism in order to shape the power. I need to reduce the speed in order to amplify, yeah? To amplify the torque. And this is actually the idea behind the gearbox. So we can see the gearbox as a counterpart for the transformer. Yeah? So here, as you can see, I'm having motor. I'm having here 2 discs engaged to each other, and I'm shaping the power from the input side to the outside in order to drive the load. Now, as in the transformer, if I'm neglecting the losses, then the apparent power and the input apparent power must be equal to the output apparent power. Here, the same, except that we said that the active power or the power, the input power, and the output power from the gearbox must be the same if I'm neglecting what?
The losses.
The losses. Yeah? You know that physically I cannot neglect the losses, but simply because the losses is just a fraction of the power, in theory I can say I don't care about it. In order of magnitude, huh? In order of magnitude. So now, so let's assume that the motor is rotating by certain speed and developing certain torque. And here I can say either it is T1, W1, and let's assume that this is N1, where N is the number of teeth. Now, if I'm looking to the, let's say, a side view of the gearbox, it actually consists of 2 discs. Let's assume the first one is the smallest one, and the second one is the larger one. And in between here, I'm having the teeth. So while the first disc is rotating, the second disc will rotate in lower speed. Why? Because of the diameter. Correct? If this one required 1 second to complete 1 revolution, the second disc, roughly speaking, 2 seconds. Roughly speaking, just in the size. No? Yes? So simply here what? I'm reducing the speed by 2, which means that I'm amplifying the torque by what? By 2. Yeah? And this is very convenient for the electric drive system, because sometimes I don't have space. I don't need huge machine. I need compact machine in order to drive a load, but I don't need that speed, so I will, let's say, install a gearbox in order to what? In order to shape the power. And here I'm having the N2. So the N1 is the number of the teeth for the first disc, and N2 is the number of the teeth of the second disc. Now, in ideal case, is the gearbox recommended or no?
No.
The ideal. No.
No.
Why?
Friction,
Yeah, the friction. Losses. What else?
maintenance.
Maintenance. Any moving part need a maintenance, correct?
Yes.
What else? Imagine that this gearbox is installed in a robotics arm.
Yes.
Now, if the robot arm hit any object, if there's a gearbox, you cannot sense it. Or it's hard to be sensed. But if there's no gearbox between the end effector, let's say, and the motor, simply you can sense the torque. There's an action torque, automatically this will prevent a damage of the object. So this will depend on what? On the application. For the regular application, as train elevator, of course, we need what? A gearbox in order to regulate the power. Now, how I can model the system? In the end of the day, I need only two mass system, which means that I need a machine engaged with a mechanical load with equivalent inertia and equivalent, let's say, viscous friction. How I can do that? You know that if I need to write the mechanical equation, which we all of us know, it's J d omega by dt plus b omega must equal the summation of the torque, let's say Te minus Ti. Simply here I'm having system 1 and system 2. And in between I'm having what? A gearbox. Now if I need to model it, I need to, let's say, find an equivalent system such that I can represent this system, which consists of machine, gearbox, and a load with a two-mass system. Yeah? Motor, load, direct coupling in between in the shaft. Yeah? Now, what's the difference between this one and that one here?
Speed the same.
Yeah. Here, the torque and the speed are the same. Here, no. This shaft has certain torque and speed.
Yes.
And this shaft has its own, let's say, torque and speed. Yeah? Now, if I need to mathematically model, I need to write two equations. And you know that this will complicate the system. Yeah? But simply, if I can do this one, and this one is equivalent.
One.
So it will be only a single equation. So I need to find what? Something we call J equivalent, or the equivalent inertia, and the equivalent friction. So I need, in the end of the day, to find a tool in order to mathematically, let's say, model the gearbox. As we said before, the input power to the gearbox is equal to the output power. So this is the first fact that I can use in order to model the gearbox. So the first one here, P1 must equal P2. So this means that T1, W1 must equal T2, W2. So simply I can describe, for example, W2 equal to what? Or let's say T2, or whatever W2 is. Yeah? It will equal T1 over T2 multiplied by W1. Yeah? Or logically I need to describe the speed, so I can, the torque, sorry. So I can say that T2 will equal to W1
T1
over
W1 over
W2 multiplied by T1. So this is the first assumption, or the first fact, that the power in and out from the gearbox is the same if I'm neglecting the losses. If I'm neglecting the losses, yeah. Now the second one, that the speed. What the relation between the speed and the number of the teeth, or let's say the diameter of the disc? If I'm having a small disc, it will rotate faster than the bigger one, correct?
Yes.
So simply this means that the speed is inversely proportional with what?
The
the diameter and the diameter actually the number of rotated. Huh?
Yes.
Circumference, I can, let's say, implement certain number. Yeah?
Yes.
So simply the second fact I can use in order to model the gearbox is that omega inversely proportional with 1 over n. So this means that omega 1 inversely proportional with 1 over n1 and omega 2 is inversely proportional with 1 over n2. Yep. So simply I can find the ratio between omega 1 and omega 2 to be equal to n2 over n1, and this in general we call it the gear turn ratio, similar to the transformer turns ratio. Good? Okay. Now, this means that if I'm having T2, I can reflect it here, correct?
Yes.
By using what? The gear turn ratio, or the gear ratios, yeah? And the same thing here, if I'm having a torque here, I can reflect it here, yeah?
Yes.
If I'm having speed here, I can reflect it here.
Yes.
It's identical to what? To the transformer. Hmm? You remember the transformer?
Yes.
The transformer actually has no direct coupling between the primary and the secondary, yeah? What we have electromagnetic coupling. But simply in order to project or to use what we know from the circuit, we need to find the equivalent circuit. Yeah? In that time, what we did, we referred. Yeah? We referred what? The secondary to the primary or the primary to the secondary according to your interest. Yeah? According to your interest. Yeah? And we find what? The referred, let's say, resistance, and we find the equivalent circuit. Here are the same. So simply, I can do that and say, for example, if I'm writing the load side, then it will be J load d omega load by dt plus b of the load multiplied by omega of the load must equal. Here, this is one, T E, the motor, or the reflected torque of the motor. Which one? This one is reflected. Why? I'm writing here. I'm writing the equation in this side. Correct? Yeah?
Yes.
So now I need to use what? I need to reflect T1, or what I call TE, to the load side. So this will be TE reflected minus T load. Yeah? And we know the relation between T1 and T2. Yeah? The same thing if I need to write the equation with respect to what? To the motor side. In this case, I will say, this is for the load side, huh? The same equation I can write for the motor side, so I can say J of the motor, D of the motor by dt plus B of the motor, omega of the motor must equal TE minus
T load.
T load. Good?
Motor side.
This is the motor side. Now, how to write the reflected torque, let's say. We know that the first one is the T1 will equal omega 2 over omega 1 T1, T2, sorry. Yeah? And we know that omega 2 over omega 1 was equal to what?
And 1 over.
Yeah, N1 over N2. So simply I will take this one here and put it here. And now I'm having T1, which will equal N1 over N2 multiplied by T2, correct? Yes? Yes? Good. So this is what? Which one? Which one? Here, I'm reflecting what to what?
The load to the
Reflected
motor.
the load.
The load to
The
the
load
motor.
to the motor side.
Yeah, so this is will be T load reflect. Correct?
Mm.
Yes? Now if I need to write TE reflected, it will be what?
And 2
N2 over N1.
N1.
Correct? N2 over N1. Good. Now, if I need to write a single equation, so I need to find something we call the equivalent inertia. The equivalent inertia and the equivalent viscous friction. Now, how I can find the equivalent inertia?
Substitute.
Substitute. Okay. What?
Integration.
Now see, if I need to write it, do you know the kinetic energy?
Yes.
Now, if I'm having a multi-system, the total kinetic energy must equal to what?
The summation.
The sum.
to-
The summation, yeah? So now what I need to find equivalent kinetic energy. The kinetic energy for the rotating mass is equal to what? 1 over 2 j omega squared, correct?
Yes.
Yes? So, I will say that the equivalent kinetic energy, K equivalent, will equal 1 over 2 J equivalent multiplied by omega
Square.
squared. This must equal to what?
The sum.
The summation. So the first one is 1 over 2 the motor side, the kinetic energy of the motor side is equal to what? 1 over 2 J of the motor omega M of the motor square plus
Plus
Half
half
J
J
of the
load.
1 over 2
J load.
J of the load
omega the load square.
omega of the load square. Now, this equivalent as seen from the motor side or as seen from the load side,
Both.
Both.
Same kind of energy for all systems.
yeah, but simply now here, I need to uniform the speed. So either the mass is rotating with the motor speed or rotating with the load speed. Now in general we refer to what? To rotate in the motor speed. Yeah? Yeah? So this one I will choose to be M. So I need to change this one and keep that one.
Yeah.
Yeah? This is mean that I'm referring to where? To the motor. Yeah? So let's assume this is, will be the M because I'm interested in referring to the motor side. So now what I need only to refer this one. Yeah? Because the first one, this one's what? Is the motor side.
Already.
And this is the load side. Now I need to refer it to rotate in single speed because I'm having two mass system. Huh?
Yes.
Direct coupling, they are rotating what? In the same speed. So this is the load side. Now, So simply this means that here, I will take this one here and say that 1 over 2 J L omega L over omega M all square multiplied by omega square. Did I do anything? Did I change the equation? No, it's the same equation, correct?
Yes.
Yeah? The same equation? Yes or no?
N
N
N not omega.
مش أوميجا L
N L
L square
1 over 2 omega M.
نص
لا N
1 over 2
Oh.
J omega J L
Oh.
N L not omega L. Right?
Yeah, I'm writing it now in terms of omega.
Okay.
And already I have the relation between omega and N. But now what? If I do a Bachmann theory, this one will cancel this one. I will
Yes,
get this
No,
one.
the same
Yeah.
equation.
I'm not substituting. Yeah?
Yes. Oh,
Yeah.
okay.
The same equation. Yes? So now, this means that I can write the equivalent kinetic energy which will equal 1 over 2 J equivalent
Omega M square.
Brass.
or
After J equivalent.
عامل مشترك Omega M square.
now this one I can write n1 over n2 squared all now multiplied by omega
M
m
square.
squared. Yes?
Right.
Yep. So now this one is what? This
You
one
mean
JM,
JM,
sorry.
JM.
No, this one's JM. I'm writing this one.
Refer to the motors.
In the first stage, I was intending to write this one, writing that one, but simply to save some ink or to save the head. You know, this one has a lifetime. So now we have what? Now we can write here the J equivalent will equal to
G M.
Jm plus
G M.
JL N1 over N2 squared.
Square.
Now the same thing, we can write it for the viscous friction, so the B equivalent will equal to Bm plus
G L.
BL multiplied by N1 over N2 squared. Yep. So now I can write what? A single, what?
Good.
A single equation. Okay. Now, N1 is what? The number of the teeth of the first disc. N2 is what?
The teeth is second.
In general, which one is the larger?
And two.
Yeah, so N1 is much, much smaller than N2. What about if a less than one number I squared?
Very, very small.
Yeah, it will be very, very visible. So in general, this can be neglected actually. Yeah? But for you, you don't neglect unless I'm telling you what? Neglect. Yeah? Now you have a mechanism in order to what? To write the reflected, let's say, equivalent inertia and the equivalent time, equivalent viscous friction. Good. So this means what? This means that now I can represent the system, this one, with a single system, which rotates with a single
Omega.
speed, and simply I'm having J equivalent and B equivalent. So I need only a single equation in order to represent the what? Let's say the mechanical system. Huh? Remember, one of the drive system, one load or one machine drive multi-loads, correct? So in this case, maybe I will have what? Not only one gearbox, three. Sometimes I will have what? Complicate, let's say motion.
Multi.
Yeah, it can be either rotating, translation, or
Pushing.
translating by rotating. Screw motion. You know the screw motion?
Yeah.
The screw actually, while rotate, it will
push.
what?
Trans-
It will transmit, let's say, yeah? Or translate. Huh? And this is what we call it a complicate, or let's say a screw motion. It will move or translate while rotate. So in this case, so I finished this situation. This here. So in this case, what about if I'm having a compound? Which means that I'm having, let's say, a motor here. Let's assume this is the motor. And this motor is connected to a load, a rotating type load. And in the same time, I'm having a mechanism that transfer the rotating into what? Into translation, such as what? How I can? The elevator, the pulley. Huh? While you are rotating the pulley, bakara. While you are rotating the pulley, simply the weight will be what? Will be translated. Huh? So let's assume that here I'm having a mechanism which transfer, let's say, the rotation to linear motion. So simply here I'm having what? A linear load. Yeah? Now this linear load has certain speed, correct?
Yes.
V1. Yeah? And here I'm having certain force, let's say F1. Now here what I'm having, a certain torque and a certain speed. Yeah? Now the same thing, what I need to do, I need to find what? The equivalent inertia and the equivalent the viscous friction. Or simply I need to represent this system into what? Two masses system. Yeah? Two masses. Motor, mechanical load. Equivalent J, equivalent B. Correct? The same thing. From where? From the kinetic energy. Now, the kinetic energy tell you what? Now, let's assume that I'm interested in which side? In the motor side. So, from the total kinetic energy, 1/2 J equivalent multiplied by omega m square. Why omega m square? Because I'm interested in what? In the motor side. If I'm interested in the linear here load, I will say V1 square. Yeah? This is where I'm interested. Where I need to refer. Huh? Must equal to what? Here I'm having two systems. The first one is rotating. The second one is what? Is translating. Huh? So the kinetic energy for the first load, which is 1/2 J load, and this one appears to be direct coupled. There's no gearbox in between, so the shaft will rotate in the same speed of what? Of the motor. Good. So this will be what? Omega m square. Plus, now the kinetic energy for the linear load, 1/2.
mv square.
Yeah, the mass, 1/2 the mass multiplied by V1 square. Yep. Correct? Yeah. Now, what I need now, I need to reshape the equation. such that it appears to be what? 1 over 2 as a factor, multiplied by certain term, multiplied by omega m squared. So here, from here, I will take what? I will divide by omega m and multiply by omega m squared. Yep. So now, this can be written as, let's change the color to be dark. So now I will respect the 1 over 2. So this will equal 1 over 2. Now here what I'm having, Al plus the mass V1 over, it's not over, it's over. Let's write it here. V1 over omega m whole squared. Now I can multiply it by omega m squared. Yes? Good. So simply now I can write what? I can write J equivalent to be J of the load
mass
plus the mass multiply V1 over omega m squared. Of course, I can find the ratio using the information from notation to translation. But simply, I will, let's say, convince myself about this equation. It's good? Yeah? The same thing I can do to find the viscous friction. So, it will be the same. I can write it as B equivalent equal V load plus the mass, or let's say not the mass, it will be the friction. It K, linear, maybe it's spring, it will be K. The friction constant, V1 over omega 1 squared. Now if I need to write this one, the B equivalent, it will be the B of the load plus here, let's assume it is a certain K constant friction, V1 over omega m squared. Good? Okay. Now, in some textbook, they use a factor here. They call it A. So this one can be written as JL plus A squared multiplied by the mass. Yeah? Okay. Now, the steady state operation. Before that, do you have any questions here? No? Now, the steady state operation. What's the meaning of the steady state operation? The meaning of the steady state operation. Do you know the meaning of the steady state operation? The meaning of the steady state operation? Speed. No? The meaning of the steady state operation? Speed. Okay. So steady state is what? When the system settles down. When any d by dt will go to 0. Yeah? According to the, let's say, the transit response characteristic, it is what? It is 5 the time constant according to what? To 5% criteria. Yeah? Yeah? Or 3 times the time constant if what? 2% criteria. Yeah? But simply because you know that 5% is okay. Yeah? Do you know why they say this definition, the steady state? The linear time invariant system will reach to the final value at t go to infinity, which means that you will stay until the day after to settle down. It's impossible. So that's why they make a definition of what? Of steady state, that the system reach this, not the stability, settle down. Yeah. Of course, it must be stable, otherwise it will escape to infinity. Yeah. Yeah. Okay. Now this point actually is what? Is the intersection point between what? The torque speed characteristic of the load and the machine. Yeah, and the machine. Okay. So let's assume that we have what? We have the following plot. I will plot here a torque speed characteristic. Yeah, this one. And let's assume this is the torque, this is the speed, and let's take the following scenario. This is the TE, I will take it TE, and I will change the color here. And say this is the TI. TI. Now, where is the operating point? The intersection point. Yeah? Where is the intersection point? This point. So let's assume that this is omega naught. I'm here. Yeah? Now you know that if the system is operating, there's a disturbance. It can be. Yeah? Now the question of stability. How to decide that this operating point is stable or unstable? Do you remember the torque speed characteristic of the induction machine? You have two regions, correct? One is forbidden, yeah, the nonlinear region. Dr. Sahel said that's what? It's unstable region. And the second one is the nice region, the linear region, correct? Stable region. Why? That one is unstable and this one is stable. Why?
The motor will deaccelerate.
Yeah.
Until reach the operating point.
So-
بتزيد torque وخلي acceleration.
So the meaning is what? If I am standing on an operating point, if any disturbance happened, this means that either the speed increased or decreased. Yes.
Yes.
Now, if I'm increasing the speed, then the system must generate what? A braking torque.
Yes.
The torque must be reducing in order to what? Deaccelerate. If the speed is below, if I'm reducing the speed, then the system must generate what? Accelerating torque. The torque must be higher. TE must be greater than TL. Correct? In order to rotate. Yes?
Yes.
If this is the case, this point is stable. Yes? If not the case, the system is what? Unstable. What the meaning of instability? A small disturbance, small variation on the operating point is sufficient to put the system to scale to infinity. Huh? You know that in engineer there is no infinity by infinity. It's large in magnitude. The machine will overspeed. Huh?
Damage.
It will damage and it will reach a speed such that the vibration of the shaft cannot handle it. Yes? Who decided? The mechanical engineer. Yeah, because they design the shaft, they designed everything, so they will calculate and say that this machine can handle twice the rating or 3 times the rating. So anytime the speed reaches that level, it's unstable, although the speed is not reaching to infinity. Yes? This is the meaning. Okay. Now this system, stable or unstable? Now the blue line is what? Is the motor characteristic. The red line is what? Is the load characteristic. And I'm operating where? At the dot, the red dot, correct? Now let's see. A small disturbance can cause what? The speed to either rise or reduce. Choose.
small disturbance speed
اختار أي جانب.
يزيد
Yeah, he chose.
ابراهيم
Ibrahim. So Ibrahim said that assume your disturbance increased the motor speed. So I will follow which line, the red line or the blue line? The blue line. Why? Because I'm discussing the motor. So increasing the speed, this is the direction of increasing the speed. Yeah? So I'm here. Now let's assume another color. Huh? Ibrahim, choose a color. اختار أصفر مش حلو. What about the green? Huh?
Okay.
Green. So I am somewhere here, here this one, I'm somewhere here. Yeah? Yes?
Yes.
Now, the motor torque, is it higher than the load or less than the load?
Less than.
So if the torque of the machine less than the load, can I accelerate?
No.
So this means that the speed will decrease until reaching what?
The point.
So I'm returning back to what?
The
So
stable point.
the stable. Yes?
Yes.
Do you see it? This one here. Now the machine will develop a torque less than TL. So this means that I should what? I should deaccelerate. So,
Yes.
so if I'm deaccelerating, the speed will reduce until I'm reaching here at the red point. Maybe Ibrahim said it's a luck. Just by chance. What about if the disturbance caused the speed to what? To reduce.
To reduce.
He chose to be
Yeah,
increased. Now it's what? It's reduced. So where I will go? Yeah. I will follow the blue line. So I'm somewhere here. Huh?
Yes.
Now let's see. Now the motor is generating a torque higher than the load.
Yes.
So I'm accelerating.
Yes.
So if I'm accelerating, I will return back to where?
The stable point.
To the stable point. So this means that this point is stable. Yeah? Okay, yeah, that's good. Now let's about taking another example. For that, let's take that opposed TL and TM. The same plot. Let's replot it here. This is the torque, this is the omega. Okay, this is the TL now, and this is the T E. And now I'm operating at the same point, let's assume. So the red here. أميرة نعم شو اسمك اللي دخلت آخر شيء؟ محمد؟ محمد. Now I am on the red point. Something happened. Load change, anything, undisturbed. Now the speed will change. Choose. The speed is, you think higher or lower?
Higher.
Higher. So I will go in which way now? I will follow TE. I will follow TE. So I'm where? I'm here or here?
Motor.
Here. I'm somewhere here. Now let's see. In this case, the machine is developing a torque higher than the load or less than the load.
Higher.
So I will accelerate.
Yes.
So this is unstable. Correct? I will accelerate. I will go to the infinity. Yeah. Yeah. And beyond, according to what? Toy Story. Buzz, you know? To the infinity and beyond. Yeah. So something like that. So let's go here. Now what about if the disturbance caused the motor to slow down? So I'm in this point now. Huh? Now let's see. The motor will develop a torque which is what? Less than the load. So I will deaccelerate. So the same thing. So it will go deaccelerate until what? Look rotor. Yeah, look rotor. The rotor will never rotate. We call it block reward. Huh? Now, the first case or the first system, the system was stable. The second one,
Unstable.
so simply we can judge. Huh? So if I give you any, let's say, torque speed characteristic interaction between the load and the machine at certain point, and I'm telling you, is that point stable or unstable? You can judge. Yeah, that's good. But you know that we are engineers, so we like the mathematics. This is what makes us what unique. Huh? So someone say, why I should build this one? Can I find a relation between the load torque speed characteristic and the machine torque speed characteristic such that I can judge if this point is stable or unstable? Yes or no? Can we do that? Yes, we can. Obama. Huh? Trademark for him. So this is the system 1, which is stable, and this is the system 2, which is the unstable. Now someone will say, if I'm operating at certain speed and I'm having disturbance, then this means that omega will equal omega naught plus delta omega. And by delta I can say it's plus or minus.
Yes.
Yeah? In the same sense, do you see that either I'm having a load, it will be plus or minus, correct? So this will state that I'm having also a variation or a disturbance where in the load torque and in the same thing in the motor. So this means that T, it's not T, it's bigger than T. Still I cannot control it. I'm getting too old. So this will be the TE, let's assume it's T naught plus delta TE. And the same thing is applicable for TL, which will equal TL naught plus delta TL. Yes? Yep. Now let's write the equation of motion, or what we call the swing equation. Huh? The swing equation equal to what? This. Yes? Yeah. What? Swing equation. JD omega. T minus T. Yeah? So simply, if I'm writing the swing equation, it's J d omega by dt will equal to T minus Tn. Now, under small variation, I can write this one as J d of delta omega by dt should equal delta Te minus delta Tn. Yep. Good. Yeah. Okay. Now I need to solve this equation. So if I need to solve this equation, I must write it in terms of what? Ordinary differential equation. Yeah?
Yes.
Now, can I say that? Now, the variable here is what?
Omega.
So I'm differentiating omega with respect to t. So if I need to let's say, organize those in terms of omega, correct? Delta is, if delta is very, very small, it will be what? For example, if I'm having delta I over delta t, if delta approaches 0, this is actually what? D by dt. D by dt, correct? Yeah?
Yes.
Now, if I need to differentiate with respect to other variable, I will not say d. شو بحكي؟ partial. So it's the same.
Yes.
Yeah, it's the same. It's not. That one is already understood to be differentiated with respect to time. The second one, I'm differentiating with respect to something else. That's why we call it partial. Yeah? No, partial. Something like that. Partial. Okay. So now, someone will say, I can rewrite delta TE to be partial TL by partial omega delta omega. Correct? Yeah. And the same thing I can do for what? For the low. I can say that partial TL, I can write it this one here. This will be partial TL by partial omega delta omega. So now what I will do, I will substitute this one here and this one here. Yeah? Yep. 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 So let's see what will happen. I have a slide more. Yeah, this one. Ah. Okay. This is supposed to be. No. So simply now what I'm having it was what? J D partial omega by partial T should equal. Instead of TE, what I would put? Partial
Partial
TE
TE
by
of the
partial omega
delta
delta omega minus
partial
partial
TL.
and this one is the okay, partial TL
partial
over partial omega
delta
delta omega. Correct? Yes. Yeah. So now this one can be written as partial T by partial omega minus
partial
TL by
partial
omega or multiply by y.
delta
And this is the first order of the differential equation. Correct? Now partial TE by partial omega is what? No. Physically is what? What the relation between this one and the slope of the torque speed characteristic?
Slope.
It's the slope. Yeah. So now let's see. Who can solve this equation? This is a piece of cake, cheesecake. Easy to be eaten. Can you solve it? Nah. I don't need to go to Laplace. I know the closed form solution. It will be omega 0 exponential minus t over time. Yes? This information we know from Dr. Saleh. Correct? We know that. Yep. Okay. So simply here, we can say that delta omega t. Now what I'm calculating the variation. It should equal to omega naught exponential. Yeah? 1 over j, I rearrange because I should put j on that side. And simply this will end up to be what? Partial t. It's not t. So this will be the partial T by partial omega minus partial TL by partial omega multiplied by the T, correct? Yeah? Now, it's logically to write the exponent in negative sign. Because if the exponent in negative sign, I know this term will decay to where? Where? If the exponent is negative, then الأس negative نروح على zero ولا عندي
zero
zero. Yeah. So, in order to make it very simple, someone will say, okay, this will equal exponential minus 1 over j. Now I should what? Exchange the position for that. Correct? So, partial TL by partial omega minus
Partial.
partial
TE
partial TE.
over partial.
I think I'm pressing one of those. Okay, let me scroll for you. So this will be partial T by partial omega multiplied by the T. So, for stability, what's the condition now? Who can tell me the condition? شو اسمك يا صبية؟ مرام. So, what's the condition of stability? When delta omega will go to 0. لما الاكسبونت تكون نيجاتيف صح؟ متى تكون نيجاتيف؟
كان بوزيتيف.
لما يكون داخل قوس بوزيتيف ماشي. Which is? Can you give me the condition? Partial TL by partial omega greater than.
Partial
Yeah.
TE over
So the slope of the load torque speed characteristic is higher than the slope of what? Of the machine torque speed characteristic. And this is mathematically the meaning of what? Why the induction machine, the first region was what? Was stable and the second one was stable. So now for stability, delta, let's say, or partial whatever. Okay, I will put partial TL by partial omega must be greater than partial TE by partial omega. Understood until here? Yeah? So let's check the first one. The first one, the slope of the T is what?
Negative.
The slope of the TL.
Positive.
And you know that the positive is higher than the negative. We don't need to be a genius. Even simple know that. بسيط فعلا. By the way, really, بسيط is genius. Do you know why? Because he's not using his brain. That is genius. Can level up. Imagine if he uses it. What about the second one?
The TE is
TL is negative. T is positive, so this one's unstable. Good? Yeah, good. Understood? Okay, what else? Example. I'm having an example. Okay. Who can read the example? شو اسمك؟ ساعدني شوي. يلا أستاذ.
A motor having a suitable control circuit develops a torque given by Tm equal A omega plus B. The motor drive alone whose torque is expressed as TL equal C omega squared plus D ABC, and the are positive constant. The total measure of the rotating masses is J.
The first one. اسمه
يزيد
يزيد. اقرا الأول شو هو؟
determine the relation between the constants A, B, and C and D in order that the motor can start together with the load and has an equilibrium operating point equivalent to rotational system.
Very straightforward. Very nice. Okay. Now let's see. Do you see TL?
Yes.
This is a combination of two loads. Which is what?
One constant and
Windage load.
and the motion.
Windage. Yeah, anything related to the wind,
Yes.
like fan. Huh? So a windage load plus what? A constant. Correct? Yeah.
Yes.
Good. So this can be a combination. Because when we discuss the load, the mechanical load, we say this one, but I can combine. Okay. Now, here what I need. I need to find the relation between all the constants such that the motor can start while the motor is engaged. Then I need to find the operating point and see if this operating point is stable or unstable. So at start, omega equal to what?
0.
Zero.
Yes.
Very simple. At start, omega equal to 0. Now we know that the equation of motion is J d omega by dt must equal Te minus T load. Now this is the T of the motor, huh?
T minus.
Yes.
Which is T, yeah? And this is what? The T of the load. Yeah? Yes?
Yes.
Now, at start, omega equal to what?
0.
Omega equal to 0. So simply in order for the machine to start up, T must be greater than Ti. Correct?
Correct. Yes.
If they are equal, they will stay there. At operating point, they will be equal.
Yeah.
Yeah? But while I'm accelerating, they will never be equal. Otherwise, I cannot move. So this will state that T is greater than TL. Correct? So this means that TE is greater than TL. Now, at omega equal to 0, T is equal to what? B, I think.
Yeah, B.
Must be greater than
D.
D. So this is the first condition. Correct? So this means that whatever later on, B is greater than D. Yeah? Good. Now, I need to find what? The operating point. Yeah? Now, at the steady state operating point, d omega by dt equal to what? 0, but omega not equal to 0.
Yes.
It will be omega naught that I'm seeking. It can be 0. I don't know. Yeah? It can be infinity.
Yeah.
Yeah? If unstable. Yeah? So simply now, the same equation here, I will say that at steady state, this means that any d by dt should go to where? To sleep, to 0. Yeah? So this means that Te should equal TL. Now I'm having what? Two equations. I will equal to each other. So I will get single equation with one unknown. I can solve.
Yes.
Yeah, I can solve. So simply now, should I solve everything here? Yeah. Okay. بدي احط صفحة بس.
On the board.
المفروض احطها ثلاثة. keep. Okay. So there's a space, huh? Now I'm making space. Now I'm making the space. So let's return to the assembly. So what I need to say that the T, which is A omega plus B. So I need to say that. So I need to say A omega plus B must equal the load, which was what?
C omega. C omega square plus D.
C omega square
Plus D.
plus this extra cheese. Plus, it was D, huh?
D.
So simply now I can rearrange this equation as C omega square minus A omega
plus D minus
Plus
and
D minus
plus D. B was greater, okay?
Yes.
So I will say this will be minus B minus D. The same.
Yes.
Yeah?
Yes.
Equal to 0. Second order algebraic equation. We have a closed form for that. Yeah, do you remember
Minus.
AS squared plus BS plus C, the closed loop is what? Minus B plus minus square.
Minus B plus minus
Square
square
root
root of
B squared minus 4AC over 3. Yep. So we can have it, so I can write it down. I don't need to say that. So simply I will get omega, if I solve this one, I will get omega will equal A plus minus the square root of A squared. It's minus,
It's B.
minus first, so plus, so it will be plus 4. I will take B minus D over the 2 of the factor multiplied by omega square 2C. Yep. Yep. Now, in order for the machine to rotate and develop physical speed, the under the root must be positive. There is no imaginary.
Yes.
The imaginary is not physical thing.
Yes.
Yeah? It's virtual thing. It's a mathematical representation for a coordinate,
Yes.
orthogonal coordinate. Yeah? In order to simplify our life. But I cannot find what something walking around is complex.
Not physical.
Yeah, it's not physics. Huh?
Exist.
So for PC
RFC.
and B minus D.
Can you see?
Yes.
No.
There's a C.
There's a C.
Yeah. You don't need classification because I was seeing the C, even if there's no C. Okay. So let's see. Let's see. A is positive,
Yes.
and for sure A square will be positive.
Yeah.
So B minus D. Do you remember
B-
our condition? B is greater,
than
and C is positive. So under the root is positive. Yes.
Yes.
So under the root is positive, I don't have problem until now. So now I'm having two options, yeah? Whether the speed is positive or negative. Yeah?
Yes.
Yes.
But simply here the speed is positive, correct? Do you know why? The torque TE is positive all the time. Or TL is positive all the time. Yeah? It's C omega squared plus D. Yeah? So in order to do intersection, then the speed must be positive. Yeah?
Yes.
So simply I must remove the negative one. Yeah? Now let's see. This means that this one has two solutions, A minus or A plus.
Yes.
Yes?
A minus.
A minus negative.
Yeah, so the speed is will be what? The plus one. So the operating point, omega, will equal to what?
A plus.
A plus. The square root of A square plus 4 the B
Minus D.
minus the D multiplied by the C over 2C. Now, is this operating point stable or unstable? Huh? Let's do the check. Yeah. So what I will calculate the first one? Partial TL with respect to partial omega. Then I will calculate partial T with respect to partial omega. If the first one is higher, then it's stable. Correct? Now let's see. Do you remember the first one was what? This one is the motor, correct? So partial TE by partial omega is equal to what? The A, correct? Yes? Yeah?
Yes.
Now, partial TL by partial omega is equal to what?
2C.
2C. 2C, correct? 2C omega.
Omega.
Huh? 2C.
2C omega.
Now, the condition of the stability is what? That this one must be greater than this one, correct?
Yes.
Huh? Let's put it there. So the condition of the stability is what? Is 2c omega must be greater than a. Correct?
Yes.
Now, do you see this one 2c?
Yes. Cancel.
Do you see this omega?
Yes.
So if I put this one here, what I will get?
A plus square.
And for sure it's greater than a.
Yes.
Yes.
Yes? Why? Because
It's
a
a
added
plus
with a positive number. Yeah?
Yes.
And by the way, the positive number is greater than a.
Yeah.
Yep, because it's
A square.
plus some.
Yeah. So simply this will be what? This will be the a plus the square root of this square root is perfect. Yeah. A square plus 4b minus d multiplied by the c, and for sure this one is greater than a. So simply this means that what to
It's
This one.
stable.
Stable.
stable system, huh? A stable system. What else? I can give you what else. Who can calculate the initial accelerating of the drive? Accelerating of the drive. Yeah. Omega is 0, but d by d omega is varied.
Yes.
So simply, this means that what? D omega by dt is not equal to 0. Although
Yes.
the speed is 0.
Zero.
Initial accelerate. I will start to accelerate, no? So simply here, I can write, I have another extra. Yeah, I have. So I can write the initial accelerate of the drive, which simply j d omega by dt should equal. Now, at the initial accelerator, omega is equal to 0. So te will equal to what? To the b, correct? And the load will equal to what? To the d, huh?
Yes.
So the acceleration is what? You know the acceleration. The acceleration is what? Is the first derivative of what? Of the speed. And the second derivative of what? Of the position. So I'm seeking what? D omega by dt. Huh? The initial acceleration of the drive. So simply here I will say that d omega now
By dt.
by dt is equal to what?
B minus
B
d
minus d
over j.
over j. Thank you. Now what about if I need to calculate the maximum acceleration of the drive? Or the maximum accelerating of the drive.
Command.
اشتق الاكسلريشن.
Yeah, now I need to differentiate this one.
Then
Then I will find what?
The zero.
Zero.
0 and to find omega.
Yes.
And from omega I will substitute it where?
And the
In the component,
acceleration.
and I will find the torque, correct?
Mm.
So this will be left for you, huh? To solve. This will be a left for you to solve. So if I only I will write it here, what I need you to do is to calculate the maximum acceleration of the drive. Simply, I need to differentiate the torque. Then I need to substitute it in the in the speeder. Simply, I'm having the equation, which is j d omega by dt. This one, j d omega by dt, which equal to te minus TL. If I need to find the maximum acceleration, I need to differentiate this one and equal to 0. From here, I will find what?
The maximum
Omega.
point.
The
Omega.
omega. Which if I substitute
T and T.
in TE,
I
I will
have
get
the
what? The
maximum.
maximum. Good. Good, 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 good. Okay. Do you have any question until here? No? Okay. The other side. Other side.